Welcome, everyone. Good morning. Good morning to the people in the overflow room. Channel surfing first thing out of the gate. Bold move. Like it. So I decided that I wanted to give this talk because back in the mid 2010s, there was kind of this industry-wide push to start moving everything to the cloud. So everyone was kind of drawn by this pie-in-the-sky dream of having unlimited computing power, unlimited memory, unlimited storage. So hey, we are no longer bound to the hardware that we're running software on. We're going to run everything in the cloud. It's going to be amazing. We're going to have infinite growth. And the thing is that a lot of these projects didn't really start to pan out. So a lot of them ran over time. They ran over budget. Some of them were canceled altogether. And I have been a part of a couple of these in different cloud platforms, in different industries. And I am very proud to say that I now have a cloud-native, scalable system running in production. But it was a bit of a difficult challenge getting here, and I have learned some things along the way, both from successes and from failures. So I wanted to take, 50 minutes and reflect on some of the things that I have learned along the way. And when I was trying to structure this talk, I was thinking about the fact that scalability kind of comes into play in the entire software development cycle. So every stage of the way, there is something to be considered when it comes to cloud scaling. And so I started to kind of structure the talk that way, but I found that I kept looping back to earlier topics and then jumping ahead. And I realized that in the same way we can't really build software this way, I couldn't really do the talk this way. So my first point is that waterfall is not going to work for a scalable cloud system. If you haven't already, you need to adopt some kind of DevOps transformation. And it doesn't really matter whether it's no-ops or platform engineering or whatever trendy DevOps replacement you particularly prefer. The point is that you need to be able to loop back and revisit the decisions that you made later. Because to build a system that can react to change, you, as a person, as an organization, as a team, also need to be able to react to change. Planning everything up front just isn't going to work anymore. There are too many variables that need to be kind of planned for, that need to be taken into consideration. And even if you have the best plan, things don't always go the way you expect them to. So when I was thinking about this, I don't know if any of you have read Octavia Butler's Parable of the Sower. She introduces this concept called Earth Seed, which is all about how the only constant is change and God is change. So I kind of feel like that is the modern cloud development fundamental principle, is that everything is change. Everything is going to change. The system is changing. So you need to be able to change with it. And that pretty much means adopting DevOps. And when my first team adopted DevOps, I worked for a large enterprise organization. We had incredibly strict standards on handling customer data. And I looked at this whole DevOps concept and I said, what, there is no way that they are ever going to let me see this super valuable customer data. We run all over the world. There's no way that they're expecting me to be up in the middle of the night making sure that the system runs. And it's a system that I probably don't even have the legal right to look at anyway. But the thing is that even if you aren't ops for production, you are going to be ops for your development environment. Because you need to know what your system is doing. If you just hand it off to somebody else, you don't really know if it's working or not. And you need to be the ones knowing whether it's working. Because you need to be able to test it. And the biggest reason that I restructured this entire talk was because I kind of wanted to put testing first, or as close to first as I could. If you take nothing else away from this, test your scaling. Test your scalability, make sure that it works. Everything else is completely moot, and you can figure it out along the way. Because if you're not testing it, you don't know what's going wrong, you don't know what's going right, and you can't change it. So One of my other principal learnings from from the years and the projects that I've been doing this is that you do not know that your system will scale until you have seen your system scale. So when I joined the project that I'm on now, basically they said, oh yeah, when the load increases, the system is going to scale out. We've designed it that way, it's going to work that way. What ended up happening was that the first time we tested this, that did not happen. So the system scaled out, and we were using app services running on app service plans. So FYI, a lot of this talk is going to be a little bit Azure leaning because I'm working on an Azure project right now, but the fundamental principles really apply to whatever cloud platform you're working on. So we were running app services on app service plans, and we saw that the app service plans were scaling out, and everybody said, oh, it's fine. The app service plans are scaling out. Look at them. You can see that they're scaled out. Everything's great. But the thing was, we weren't actually getting any more traffic through the system. And what actually was happening was that even though the app service plans were scaling out and the apps were technically scaling out with it, they weren't actually, the second instances and the third instances, all the way up to the nth instance, weren't actually starting correctly. So even though everyone said that the system was scaling, it wasn't really scaling. So I have a good friend who is also a developer, and my friend's husband is completely non-technical. And so he ends up having to hang out with a bunch of developers talking shop and talking about technical things. And kind of his little party trick is whenever things get a little bit too complicated, he throws in, yes, but will it scale? And the thing is, it's a good question. But what he should be asking isn't will it scale, it's does it scale? Because until you have tested it, you cannot say that it does scale. So how do you test it? When we first found that our app service system wasn't scaling the way we thought it was, basically we just had a developer who had written a script that hit our system over and over and over again. And it was during a low period, renewal in between Christmas and New Year's, and we basically found every single developer in the company who happened to be working on those days, and we gave them this script, and we said, could you please run it? And so everybody started hitting the system at the same time, and it triggered the memory load and the CPU load, and so we started to see it scaling and found out that it didn't actually work. And the thing is that is not a very elegant solution. But the thing is that any testing is better than no testing. So just start with something. Just find a way to put load onto the system, and it doesn't have to be the greatest solution, and it doesn't have to be the final solution, because just like the system that you're testing, you can change it. So find out what works, find out what doesn't work, and practice continuous improvement on your testing cycle as well. Another question is when to test. And of course, the ideal answer is to test after every single change. In reality, that's probably not going to happen. Usually load tests end up taking a little bit more time. You can't necessarily run them on every single push. More realistically, test it before every release, even if you have really short release cycles. So every day, every week, depending on how long your tests run, depending on how often you release. Consider having a load test smoke test suite. So take your most critical pieces or the things that go wrong the most often and test them as often as you possibly can. Because the thing is that it's easier to identify problems if you've only made a few changes when the problem shows up. And this is one of those things that we have learned the hard way. So my team has grown over the last year, and we have some growing pains with it. And we got to the point where we had lots and lots of changes going in at the same time, which is great from a productivity standpoint. But then at some point, the load tests started showing incredibly problematic performance results. So things just weren't working. And the problem was that because we now had more developers than we had had previously, it meant that we had more changes that had gone in than previously. So we basically had to pick apart everything that had been changed in that past sprint and take everything out one by one and keep retesting and retesting until we figured out where the problem actually lay. Then we had to take that out of the release and put everything back, which really ended up just kind of costing us more time than it would have been if we had just slowed down and made sure that we tested each of those releases one by one. So one of the things that we're doing now is that we are flagging any kind of change that we think has a high potential of impacting the system, and we're doing a little bit more planning upfront to kind of make sure that we have the opportunity to test in between each of those changes. So why is testing so important? I think it should be obvious, but no matter how much you plan for, there is going to be something that goes wrong. You probably aren't going to think of every single thing up front. We are human. There are a lot of variables in a cloud system. If you're running on PaaS, you have all kinds of connection points. You have all kinds of nuances of the services that you are building on. It's just unlikely that you are going to be able to figure everything out ahead of time before you test that it's actually working. This is actually a quote from Robert Burns. It was originally written in Gaelic. I'm going to make my, or Scots, maybe Scots. I'm going to make my best attempt at the original so that you have something to laugh at later, which is, the best laid schemes o' mice and men gang aft agley. And I think it's a very valuable piece of information to remember in English, or if you want to translate it into Norwegian, I will let you do that. But it's good to keep in mind, because no matter how well you have planned, there is a very good chance that you have missed something. So unfortunately, I have an example of this one too, which is that I work on a system that basically does a lot of data indexing. And we needed a way to be able to kind of restructure that index when we needed to. So to be able to shift from one index schema to another in live production without impacting anything, and preferably as soon as possible, in the shortest amount of time as possible. So we sat down and we looked at our system and we came up with some fantastic sequence diagrams, and we figured out where we could inject the transition code and how we would actually make this work. And we iterated over the design, and we had a couple of developers who were discussing it and throwing in ideas, and we said, oh, we can use this new technology that scales faster than what we are currently running on, and if we do this, it's going to be super fast, and we're going to be able to do this transition in like a very, very small amount of time. And we built it, we developed it, we tested it in our development environment, and we handed it over to our staging testing environment. And the first time we actually tried to run it at scale, we hit the problem that we had not seen coming, which is that it actually ran too fast. So all of our computing was happening super quickly, and we were plowing. We had, designed it so that we could break this giant workload into small pieces and run them all in parallel and scale out to handle all of these little pieces of work that needed to be done. And we ended up exhausting the socket limits on the data storage that was actually feeding data into the indexing. So then we had to basically scrap the entire beautiful too fast design and find a way to explicitly slow it down so that we could actually get through all of the data without exhausting that socket limit, which was, number one, frustrating, number two, terrible for the timeline, and number three, just heartbreaking because we had spent so much time on this thing. And it was too fast. How often does something run too fast? So another point in testing is that it is worth testing on as close to production specs as you can. This isn't always possible. Sometimes production systems are hugely and prohibitively expensive. I recognize that. But if it is at all possible, it is worth testing on the same kind of specifications, the same hardware, the same service tiers that you're actually going to be running in production. Because if you aren't actually testing the system that you will be running in production, to some extent, your tests are actually going to be a little inconclusive because things will behave differently. You will probably find bottlenecks in different places. So ideally, yes, test the same thing that you're actually going to be running in real life. That also means testing the same load that you were expecting in real life. It can be easy to overestimate the amount of load that your system needs to handle. That's not a terrible problem, but it could mean that you are wasting resources, that you're spending too much development effort handling something that isn't actually going to happen. But of course, even worse is underestimating, because then who knows what's actually going to happen when the system really starts running. Another thing to consider is that it's very easy in load testing to build in kind of spikes of activity. And there's a lot of talk, especially if you're working on a scalable system, that, oh, the whole point is to design the system so that it can handle those activity spikes. Something exciting happens in the world, and all of a sudden there's more traffic on your system than you were expecting. But the thing is that those aren't really, there's a difference between a spike and a cliff. And load testing can often go from 0 to 60 in 0 time. And that's not necessarily what's actually going to happen in real life. Maybe it is. Maybe you have some kind of, you're selling concert tickets and they go on sale at a specific time, so you go from no traffic to all the traffic. But for a lot of scenarios where we're talking about spike traffic, we're actually just talking about a really steep escalation. So think about how your actual traffic patterns, including those spike scenarios, are going to work, and try to design your tests to mimic that. Because if you are designing a system that is going to go from if you're testing a system that goes from 0 to 60 in 0 seconds, then you're going to end up building a system that goes from 0 to 60, and it can really be difficult. So you're going to make decisions that maybe aren't necessarily the ones that you would be making if you were actually looking at realistic traffic patterns. So yeah, think about how fast that traffic load or whatever you're scaling for is actually going to increase. But yeah, when it comes to figuring out that expected load, it's hard. A lot of the time, product owners don't necessarily know the numbers. So if you have the opportunity, try to observe a real user, especially if you're taking a system that already exists and you're building a new version. It is invaluable to actually see someone using the system. Preferably an expert user who's going to do those things that happen at speed that you may not get from a developer clicking around testing the things that they've been working on. So I work on a system that does, among other things, it runs a picture desk for large media organizations. So as news feeds are coming in, as photographers are taking pictures of world events, all of those are being fed into the system, and then the newsrooms can look at them and figure out which pictures they're going to use in production, which pictures they're going to save in their archives, things like that. And we were very, very fortunate to have one of those big newspapers let us sit down with one of their senior picture editors, photo editors, and actually watch her work for a few minutes, 15. I think we had a half-hour schedule with her, and she really wanted to explain what she was doing, like why she was clicking on things, because she's a journalist, she's not a software developer. Why would a bunch of software developers want to watch her work for half an hour? So she was saying, oh, well, I'll do this because of this reason, and I'll do that because of that reason, which is super useful from a product development standpoint, but from a scaling standpoint, really we just kind of wanted to know, how do you actually work? How fast do you scroll through that? How often do you click on those things and drag them over there? Like, within this 1 minute time frame, is that how fast you would actually be doing that? And she, of course, thought these questions were very strange, but we got so much information out of it. And we had one of our QA automation engineers with us, and he took all of that information back, and he basically codified it into our load tests. So now we have an automated system that basically simulates, 50, 100 versions of her using the system. So that way we know with a little bit more confidence when we go into production that if something happens and the entire world news organizations pull everybody in to work on it, that we can actually handle it. And the last piece of testing based on reality is use a real-world data set. So a lot of the reasons that we started to move to cloud-native development was to be able to handle larger data sets than we can on on-prem bare metal systems. That means quite often a lot of data. It's not always easy to find that much data. So one of the options for working around that problem is, if you can simulate it. So we don't actually have giant news organization media streams coming into our test system. So we don't actually have as much information as we would in a real world scenario. So we work mostly with metadata, which is information about pictures that gets embedded into the picture as XMP. And we were originally testing with images that didn't really have that much metadata, which meant that we weren't really stressing our indexing system to the level that it would be in the real world. So instead, what we ended up doing was taking kind of some of the pictures that we do have, we can inject information into them, even if it's completely nonsensical. At least we have data that we can kind of fill our indexes with to see what happens when we have more information stored. But also we were able to get a smaller set of some photos from Reuters that have kind of the realistic information that you would find in these newsfeed photos. So then we could take that small data set and basically just extrapolate it and end up making a much larger number. So I think we started with a few, like maybe 1,000 pictures, and we managed to extrapolate that out to a couple of million. In other cases, you can't really fake it. So earlier, I was working on some geological modeling software, and that is not necessarily information that a bunch of software developers are going to be able to fake easily. You can't just lorem ipsum your way through geological layering. And we had a test data set which was based on publicly available data. But the problem with the publicly available data was that it was a lot sparser than what our customers would really be working with. So we were trying to feed it through the system, but whereas an actual commercial environment would be having tons and tons of data coming in from each of the data points that we had available, we had a very, very small subset of that. And so we found that the system wasn't really behaving the same way as it would when we actually gave it real data with all of the fidelity that comes with actual commercial production data. So even though we're still talking about testing, designing load tests is actually one of the best ways to clarify the load requirements. So yeah, defining load tests helps define the requirements, because your product owners don't necessarily know how to come up with such abstract numbers. You say, well, how often is this going to happen, or how many users are going to use this, or how fast are they going to be working on something? Those are better questions than, well, how much load does it need to accept? Because if your product owners are coming from more of a business or domain background, they probably aren't going to be able to say something like, oh, well, we're getting X number of requests per second, so that's, let's add 10% as a margin of error, and that should be good. Especially if you're working on a system that doesn't already exist. So if you're kind of greenfield project, then you really need to start having these discussions. If you have the benefit that you're actually working on a replacement for a system that already exists, if you have good usage numbers for that, then that is a very, very good place to start. But basically, if you start talking about the load testing early, you will start having the conversations that you need to have a lot earlier. And it's important to start those conversations as early as possible so that you don't back yourself into a corner. And speaking of backing yourself into a corner, do not let people front load features, because there's kind of this historic model of software development, which is, okay, yes, we have this piece of functionality, and when they're all done, we're ready. But I think we've all gone over minimum specs enough that we understand the concept, but it's worth repeating it in the context of scalability. Because a million features that don't work at scale are a million features that you are going to have to refactor. And the thing is that you don't even know if you're going to be able to refactor them, because if you have to make some kind of huge fundamental change to the infrastructure in order to support the scaling numbers that you need, it could be that that shiny little piece of tech that was handling some fantastic new feature that everybody was in love with isn't actually going to work at scale, and you may not actually be able to deliver what everyone thought you already had. So it's important to iterate over your design, because you are going to learn things along the way, and you are going to have to make those changes. So even if you think that something worked up front, even if you So if you think that it worked up front and you find out that it didn't, you're going to have to go back and design. But as you're designing, you may actually run into some of those limitations ahead of time. So basically, the idea is that don't set anything in stone and just reiterate over everything. One of the things that is worth designing up front, to the extent that you can, is your infrastructure, because infrastructure isn't always, you can always change it, but it isn't always easy to change it. So I had no idea before I started putting this talk together that you could actually change a tire on a moving car. I am very impressed. I do not think I want to be doing it. Unfortunately, in my real job, I am going to be doing it, because even though we have a commercial system, we do actually have some things that we need to change. And it is incredibly more complicated to change them as things are running. So part of design is, of course, testing. So if you are looking at a piece of infrastructure, build a proof of concept, test your proof of concept, and do whatever you can to de-risk those decisions, because it's going to be very, very, very difficult to change them later. I'm not saying it's impossible, and I'm not saying that you shouldn't do it. I'm just saying that you may be the guy hanging out of a car changing a tire on the highway. So when it comes to designing for scalability, a few general guidelines is, of course, fail fast. Don't spend so much time on something that you end up losing all of that time if it isn't going to work out. It's better to know sooner that something isn't working than to get too far down a road and try to answer all of the questions and then find out that it's not going to work. So right now, I told you that we are changing a big piece of infrastructure in production. And the thing is that a lot of the devs on my team keep looking at every single little nuance and every single little detail and trying to answer all of the questions about, okay, well, if we switch to this piece of infrastructure, how are we going to change this? What are we going to set that to? Is it going to work here in exactly the same way? We need to figure out a setting for this particular property. How should we set that up, and how can we determine what that should be? And the thing is that these are a lot of decisions that need to be made, but they don't necessarily need to be made now. So we need to find out first and foremost whether this is going to work at all. And then once we have an idea that it's going to work, and once we've tested that it's going to work, so we know that it will actually do at least some of the job that we have asked it to do, then we can start going back and answering those little detailed questions. And yes, there is a chance that maybe one of them will end up being a blocker, but chances are that they're just things that we need to sort out. They're things that we need to test, they're things that we need to iterate over, and they don't necessarily have to be decided up front before we make the go, no-go decision. Kill your darlings. This is a term that actually comes from writing fiction. And it's basically a guideline for writers to be ruthless in their editing. And the idea is basically don't get too attached to particular pieces, designs, in the case of fiction writing, little bits of prose that you're absolutely in love with. The idea is to keep the big picture in sight all of the time and just not to basically do your design around the thing that you don't want to get rid of. And if you've worked in software long enough, you probably have met somebody who has some little piece of code that maybe not everybody loves, but they have poured their heart and soul into it, and they are going to keep it around no matter what, no matter how hard it is for anybody else to work on it, no matter how unreadable it is. And the thing is, we need to kind of step away from that mindset, and we need to just say, okay, you know, I really like what we've done, I really like what I did before, but it's time to let it go and move on. So yeah, the TLDR version is, if it isn't working, let it go. And don't assume linear growth. So when you're designing, there's kind of this idea that, okay, well, with one instance of the service running, we can process n requests per second. With 2 instances of the service, we can process 2n. Surely 3n, 4n, it's going to extrapolate. And I think if the mythical man month has taught us anything, it is abundantly clear now that adding a single instance does not necessarily lead to linear growth. Compare adding one more developer to adding one more service, and the number of communication paths are just going to increase exponentially. In some cases, yes, linear growth is possible, it is straightforward, and it is easy, but basically don't assume that. And a better guideline is just to not assume anything. Test it, find out. So the design questions kind of come back to the who, what, when, where, why. And for the what, it's worth asking yourself what needs to scale. So not everything actually does need to scale. If you have something that's running as kind of a one-off process, some kind of system configuration, it probably doesn't need to scale out with the amount of load that the system has or the amount of growth of the system. Maybe it does, maybe it doesn't, but it's worth actually asking yourself, does this actually need to scale? And if it doesn't need to scale, then unless you have a framework in place that makes it come for free, don't spend extra time making it scale if it doesn't need to. Again, you're going to test it, so you're going to find out later if it needs to scale, and if it does, then you can add it in. And how to scale. So there are 2 different concepts of scaling, and in case they are new to anyone, I will go through them briefly, which is scaling up versus scaling out. And I'm going to give an example with planes, because I really like airplanes. I used to fly a lot back before the plague. And this is a little Embraer, and it's an Embraer 170. I come from the Midwestern US. They use these to get from place to place because there aren't a lot of people traveling in the Midwest. And an Embraer 170 can carry 78 passengers. And yes, I am aware that an airplane cannot fly that high, so this is not to scale. So you have 78 passengers fitting on an Embraer. What happens if you actually need more traffic? Something happened in the Midwest, and now all of a sudden, people are going from point A to point B more than we had anticipated. The easy option and the straightforward option is to scale up, which is basically we run a bigger plane. Now we have an A380. It carries 853 passengers. That's a lot. It was super simple. Okay, logistics aside, because I know that actually running an A380 out of an airport is very difficult, but conceptually, all we did was make the plane bigger. The pros, it's easy. It's straightforward. The cons, maybe we don't actually have 853 passengers and that plane is flying empty half the time. It's very difficult to adjust, and one of the biggest cons is that there is a hard limit. So the A380 is currently the largest passenger jet out there. So if you have more than 853 passengers, this is not going to be a solution that works. Leaving beside the fact that we probably aren't going to run it at full capacity, which means that we are wasting a lot of resources running such a big plane. The other option is to scale out, which very simply means that we put more planes on the route. The advantage here is that it's adjustable. So, you know, we have more traffic, we can run more planes. We have less traffic, we can run fewer planes. The cons is that it's a lot of added complexity. So which plane do you put each passenger on? When do you know that you're going to need more? When do you know that you're going to need less? And how do you maintain an even distribution across them? So some things that you would want to scale up, or probably would want to scale up: throughput. We run with a Cosmos DB database, which is basically a pay-for-what-you-use model. So when we actually need more throughput, then we scale up the throughput on the database access. Storage, pretty obvious. You need more disk space, you use a bigger disk. And for intensive computation, and this is one that kind of was one of the myths of the cloud, which was, oh, we have infinite computing power. And in some cases, this is actually true. If you don't actually want to pay for a whole bunch of users to have really, really high CPUs, then yeah, you can build a system that basically rents them from someone else, and you can actually give them more CPU power for things that actually need more CPU power. For scaling out unrelated tasks, the obvious one is network traffic. So if you have 2 unrelated network requests, farm them out to 2 different instances of the service. Similarly, I mean, everybody's been harping on microservices for years, but this is one of the reasons for that is if you have 2 different services that are doing 2 different things, put them in 2 different services so that they can run separately. You're not competing for computing power between the 2 of them. You're not competing for resources. Independent data, if you're working on some kind of per customer data model and you're getting too much data for whatever component you are storing things in, consider farming that out so that you end up with 1 instance of that data storage solution per customer. If you have unrelated data that doesn't need to live together, you can do the same thing. And the last one is the divide and conquer algorithm, which is kind of where the promise of cloud scaling comes into play. So my first cloud project was actually to take a very computational intensive algorithm and start running it in the cloud so that we wouldn't have to have the limitations of storing the data on on-prem hardware. We wouldn't have to force our customers into paying for really, really large-scale processing specs. We could run this in the cloud on incredibly high-powered CPUs, and we could store all of the data in the cloud. And the storage part worked out, but the computation was still a big bottleneck. And the thing is that we had basically just lifted this computationally heavy process and just started running it on cloud computing. And maybe what we should have done is figure out if there was a way that we could actually have broken that down and farmed out part of that computation into different pieces. So if we had adapted it into more of a divide and conquer algorithm where we could actually split it across multiple services, multiple CPUs, we probably wouldn't have had that bottleneck. I don't know if it's possible. Maybe it is. I hope that it is, and I hope that that has happened, but we'll see. So the last one is when to scale. And this is kind of one of the most challenging problems, is if you are already hitting your limits, it's probably a little bit too late. So basically, you are being asked to forecast the future. And that is a very, very difficult problem to solve. Some infrastructure scales automatically. That stuff is great. I love it when you can just say, okay, yeah, if you need more resources, please take them up to the hard limit so that we don't go broke. Not everything has that ability. So when you're thinking about when to scale, consider the bottlenecks. Most often, that's going to be memory or CPU. And learn from experience. And the way you get experience in the way that you get input is by monitoring. And yeah, I actually have some colleagues who really don't want to do anything operational related, and they think that should just be farmed out to another team. But the thing is that monitoring generates the input to iterative development. because testing doesn't really add much value if you don't actually know what's happening. So you need to be able to monitor the system when you test the system so that you can actually learn from the system. And one of the first questions when you talk about monitoring is, what should you be monitoring? And the short answer to that question is just monitor everything. It is much easier to just get all of the data and look at all of the data and then filter out what actually makes sense and what's important. If you aren't sure what you need, take what you can get. Learn what kind of information is useful. And like everything else, iterate over this. Just because you're monitoring something up front and you find out that it has no value and you don't need it, then you can take it out later. If you find that you don't have something and you need it, then you can add that in later. So this is actually the monitoring for the system that I work on now. And you can see that it is a huge amount of stuff. And the thing is that the most valuable thing about, or the most valuable aspect to having so much stuff is that you actually just kind of learn to see the trends rather than the actual data points. So when something goes wrong, we can look at this huge amount of colorful curves and just pinpoint the one thing that is out of the ordinary, the one thing that doesn't look normal. So this is actually a Grafana dashboard that we have built. Again, I'm working on an Azure system, so this is going to be a little bit Azure-centric. But basically what this has done is we use Grafana to just take all of the Azure metrics that are available directly from the PaaS components, and we just aggregate them all into one single dashboard. So at the top, we have API requests for all of the different microservices. We have scaling information, so how the app service plans are scaling. We have per instance CPU and memory usage so that we can see the CPU and memory for each of the instances that's running when we're scaled out. We have memory stats. We have CPU stats at the service level, at the app service plan level. We have information about how many messages are going through our event queues. We have information about how all of the different collections in Cosmos DB are consuming throughput and how much of that throughput scaling is actually happening at any given time. We have information on how many Azure search queries we're getting and how much latency those are having. And of course, we also have our standard app insights and our Elastic logging. And the thing is that, yeah, this is a lot of information and it's scattered across a bunch of different places. But part of that is because we are still learning and we don't know what data is actually going to be useful at what time. So until we spend the time to build an amazing, perfect, fantastic dashboard, that isn't really going to solve many of our problems, because the thing is that we need to be able to change it. So one of the things that was on that Grafana dashboard was the per instance memory and CPU. And that came out of the fact that back when we were dealing with the app service, clicking on things that I shouldn't be clicking on. So yeah, back when we were trying to deal with that app service plan, app service not scaling correctly issue, that was how we figured out what was going on, was that we started monitoring the CPU and memory usage of the individual instances of each of those app services, and we could see that something was wrong because we weren't actually getting CPU numbers or memory spikes on the subsequent scaled out instances. And it turns out that the subsequent instances weren't starting up correctly. So by looking at those numbers, we were able to diagnose the problem. Could we take it out of the dashboard now? Probably. Most of the time, it's easier to just overlook it than it is to completely remove it, because we might have to put it back. And yeah, that is not a dashboard for operations if you have a dedicated operations team. So we have a separate dashboard that is for 24/7 support. It has different numbers on it. It has different metrics. It serves their needs. Our monitoring serves our needs as developers. And so yes, iterate over your monitoring. If you need to make changes, go ahead and make those changes. Maybe someday we'll actually integrate all of the different data sources that we have, put app insights, put our Elastic monitoring, put our Grafana dashboards, put it all together. We haven't had a need to yet because it's a nice to have. But we have made changes. The elastic monitoring includes some extra information that we don't get out of the box from Azure. We needed some information about traffic that was coming through the gateway. And so we built a separate dashboard just to be able to aggregate that data and process it. So iterate your monitoring. And yeah, there have been a lot of DevOps cycles on my slides because reiterating over things is the key to dealing with change. So now it's time for this talk to loop back and reiterate one more time and tell you that if you test early and if you plan for change, then your cloud development project can be grounded in reality.